Welcome to Introduction on Differential Amplifiers. In this video we will have a look at the advantages and disadvantages of using differential amplifiers, some applications, common mode and differential mode operation, common mode rejection ratio, then we will have a look at two basic differential pairs and a demonstration simulation just to show um, of what we are talking about in this video. So, the advantages of using a differential amplifier is first and foremost, and the one why it was invented, is noise cancellation. Okay, so this is one of the things we will look at with common mode and differential mode operation is noise cancellation. Then obviously the subtraction of signal. The differential amplifier is basically a subtractor. So with some feedback, it opens a lot of possibilities. It's also the input stage of operational amplifier would be a differential amplifier. Okay, your differential amplifiers have nice linear operation. It also has a 6 decibel increase in input range, so double basically. Increased input impedance, it's usually double because it's the input of two MOSFETs or two BJTs. And the one why it's so attractive is in IC applications is that there is no need for bypass or coupling capacitors in full differential mode. In single-ended, you might need a small capacitor on the output to get rid of some of the DC offset. Any case, some disadvantages is its complexity. You're going to use multiple transistors to design one of these. Two for the differential amplifier itself, one for the current source, two for the current source if you're not doing any Zeners or whatnot. And if you want to go single-ended, it can be up to 6 transistors per differential amplifier. But for the beginning, we're just going to look at some basic configurations and not go too deep into the current sources yet. Okay, so more transistors means more thermal noise. You're gonna have to do your biasing properly for these amplifiers. Typically a current source design, and note that you need transistors that is closely matched, or else you will have output offsets and bias current offsets of the BJTs. So a little bit of disadvantages, but the advantages outweighs most of these disadvantages in any case. So some applications, first and foremost, it's input stage of operational amplifiers. Then you can use them for line drivers and receivers, noiseless volume control, automatic gain control circuits, amplitude modulation circuits, and this is not while using it as op amps. This is pure differential amplifier applications. Amplitude modulation, single-ended or fully differential output. So you don't need to do a fully differential output. Weinbridge oscillators and Colpitts oscillators. Right, so differential and common mode. That is one of the topics that's going to feature while designing and analyzing one of these amplifiers, and it takes some explaining. So let's say we have two wires running through a factory or a room, whatever, from one side to the other, and we have some form of sensor, and then we need to amplify our output. Okay, so I'm just going to use the op-amp symbol to represent this amplifier with a single-ended output here, but in any case it doesn't really matter. Your sensor or whatever will create a signal with a path and a return path. Okay, so basically what you will have with a voltage source, you have a path and a return. But since the signal goes through some sort of factory floor, can have noise sources, electromagnetic interference. This is the area of power cables, so 50 hertz or 60 hertz. Long cables becomes transmission lines, and all of those gets induced on these two wires. But the nice thing is the same signal will get induced on both wires at the same time, and they are traveling in a similar direction. So coming into your amplifier, we have our signal input, we have our noise input, and on the non-inverting side here we have our noise input, but our signal is a returning one. So if we do some subtraction, we can get rid of the noise signal and amplify our sensor or our value that we are trying to receive. Okay, so that's why I say line drivers and whatnot. There is some applications in the medical field for this. So main feature is getting rid of common signals. So this signal is common to both inputs of the amplifier, and the sensor right here, or our signal that we want to amplify, is differential. It in both directions. Right, so with our amplifier, if both sides are grounded like this, we have a differential input. So our signal gets amplified by our amplifier. So this is just our output voltage here is the gain of this amplifier and the difference between the signal. So if this is a ground, we will only have our signal being amplified. Right, so our differential gain, or AD, of our amplifier denotes our amplifier's ability to amplify a signal. The common mode is when we will take a single source and connect it to both inputs at the same time. Logically, if we subtract one signal equivalently with itself, our output should be 0. Right, this is the ideal case. This is when everything in your amplifier, every transistor, every resistor is 100% perfectly matched. We will have a common mode gain of 0. Okay, so any noise and all noise will be rejected then. But typically this is not true, so there will be a very small gain in any case. Typically this gain should be less than 1, where your differential gain should be in the hundred thousands, millions even. Okay, so differential gain higher than 1, common mode gain less than 1. You do get amplifiers like the TL074 where the common mode gain is something like 10 volts per volts and the differential gain is 200,000. But both of those will get reduced when you apply feedback in any case. Right. So common mode gain is the ability of the amplifier to reject common signals or to suppress noise. A typical setup in a simulation could be one signal being a positive, the other signal being a negative, taking your differential mode signal, so the one that you want amplified, divide by 2, inserting it on both inputs, and the common mode here is right here in between the two. So this signal will be injected on both inputs. Okay, so VP, the non-inverting terminal, is a common mode signal plus half times the differential mode signal, and our non-inverting is the common mode subtract half our differential mode input. And if we do VP minus VN, so do the maths there, we get 0 plus our input differential voltage. Right. This brings us to common mode rejection ratio. Common mode rejection ratio describes the signal to noise ratio of your amplifier, and it's a comparison of signal powers. So the common mode gain, typically less than 1, the differential mode gain, typically larger than 1, rather in the range of 10 to the 6. That will give us our common mode rejection ratio. So typically this is the absolute value of the differential gain divided by the common mode gain, and you will find that this usually gets expressed in decibels, so just 20 logs of a absolute. The common mode gain is usually a negative gain, so minus 0.01. That just means that it's a inverted output. So that's why it's best to include the absolutes, just to remind you not to use the minus signal and that you actually get out the answer when doing your log and not an error. Right, here is just something from a data sheet. So this is TL074, and the gain here is typically 200 volt per millivolt, so that's 200,000, and common mode rejection ratio of 86. Okay, this means that this TL074 has a common mode gain of roughly 10 volts per volts if you go and do the maths in reverse. Right, so if you want to know what to look for in the data sheet, AVD and CMRR, sorry. You can also find this information in the temperature plots if it's not included in the parameters. Right, here is two basic differential amplifiers. So half of a signal on the one input minus half of a signal on the other input. So this is the non-inverting, this is the inverting. And if you look at the fully differential output, viewing just half of this amplifier, this is a common emitter amplifier, right? So the output from plus VID over 2 will be inverted. So this is the inverted output, and on this side is the non-inverted output. Okay, so fully differential, you will place your load here in between. Single-ended mode, you will just take one of these outputs. So if you take the one on this side, this is your non-inverting, this is your inverting. If you were to take this side, then the inputs definitions will kind of swap. Right. So as you can see, this is a common emitter amplifier, and a common emitter amplifier biased by a current source. This could be replaced with a resistor. This just means that it's a bias of some form. And the MOSFET looks exactly the same. Right. So these two amplifiers is static, right? If our two inputs are grounded and both of these transistors conducts evenly, the current from this current source will be divided equally between the two half circuits. Right, so that is one of the main points when analyzing one of these, is to remember to divide the current you get down here by 2, and most of the calculations will look fairly straightforward, like a common emitter amplifier. There's a bit more to it, but if you view it from that viewpoint, you will see that the maths work out exactly the same. Okay, so now I'm going to go over to some simulations to show what I have been talking about for common mode and differential mode. It's a bit more, it's better if you do a visual of it. Right, so my first simulation here, I've used two in quad 2 transistors, 5.6 kilo ohm resistors up here. I put my load in between the two outputs. So this is inverting and non-inverting. Inverting side, then this will be a non-inverting output. But in any case, and I placed the capacitors just to show that if I take a measurement here, that is a single-ended conversion. So if you remove this resistor and just take this to a load on this side, that is your single-ended conversion. Right, so our input is divided into two, so our differential input signal is 10 millivolts. Our common mode signal here is 2 volts at 50 hertz. This is at 1 kilohertz. And we have our current source, and in parallel with it we have some form of resistance. Norton sources usually have resistance, it's not infinite. And if you construct a current source using a transistor, it will also have output impedance like this, and this is typically responsible for your common mode rejection ratio. So we do a simulation and have a look at the signal right here. We can see that we have a very large signal. If we measure it here, you can see that this signal tends to get a little bit fuzzy, and that is due to our very small input that's being added to it. Now, if we take the output, I'm first going to look at the single-ended output. So basically the output just on one side here with the DC removed. You can see that here is the input signal, but what we have left over is our 1 kilohertz signal, and you'll find that there is a little bit of leftover from the common mode input. Right, so from this signal right here to a very simple output like that. Okay, so the 1 kilohertz signal is amplified by the gain of this amplifier, and the common mode signal, the 50 hertz one, is being suppressed. It is still present, but it is being suppressed. Okay, so that is a single-ended output. Differential output is when we would take this node and this node and see that they are nice and out of phase. And if we add another trace here from V1 minus 2, so taking a differential output, there we go. So our two outputs is out of phase, and you can see the common mode signal on them. But if we subtract the two, basically take the voltage across the load, the DC gets subtracted, it's gone, it's now at 0, and this signal has doubled in size, and you can see much less of the common mode signal on this one. Okay, so fully differential mode has less common mode signal getting through. So that's one of the plus points of fully differential. Single-ended mode, you still get a lot of common mode signal coming through, and the gain is half because you're only using one half of the amplifier for single-ended conversion. Right, so that is the basics of a differential amplifier. We will get into mathematics more in a different video. Let's open some of the other simulations that I have. Right, so here is the same amplifier with a pure common mode input. Note that I just took this very large signal, 1 volt, 1 kilohertz, and connected it to both inputs. So that is how you test common mode alone. So here for single ended output, or just one side, so there's with DC, here is without the DC, you can see that there is a very large signal here, but it is much less than 1 volt, right? So this is a bit above 24, halfway, let's call it 26 millivolts. So 0.026 volt per volt is the common mode gain of this amplifier. So whatever you see here, divided by 1 volt peak. Right. If we look at this in fully differential, just change one of these, minus V1. The signal down here at 0 volts is our common mode gain in fully differential. So you'll find that there is no DC offset on this, and there is no common mode signal present at all. Okay, that is due to our transistors being perfectly matched and our resistors being perfectly matched. If we were to go and change this resistor right here, we suddenly have some offset and we have a common mode signal present. So your components being matched in fully differential mode is very important. Okay, single-ended mode, you can hardly see the difference due to this mismatch. Right, let's go on to a differential mode simulation. Right, in this simulation I didn't go with splitting the two sources into two. I just kept this to 10 milli. Applying it like this, or breaking it out into two sources, it doesn't really make a difference. So 10 millivolts in, almost 1 volt out, single ended. If we do differential, this should double. So it's node 2 and node 1. And almost 2 volts peak. So this amplifier has a 200 volt per volt gain roughly. Okay, and that is differential mode. If we start to change these values a little bit and have some discrepancies between them, Only difference that we will see is the offset of our signal. See, it moved up a little bit. Right, so in single-ended, who cares? But with our differential, our signal will have a little bit of a drift when we have mismatches in our components. Right, and that is it for our introduction on differential mode amplifiers. The next two videos will be on the analysis for a basic MOS differential and then a basic BJT differential mode. Thank you for watching.